lecture of part 2 of section 5 module 1 of several variable calculus. So in today's lecture we are going to prove the norms in Rn. So first we are going to show that this norm 2 is a norm on Rn. So first we recall about the definitions of norm2 or Rn. So let x belongs to Rn, then the function's norm2 is defined as square root of x1 square plus x2 square plus xn square. So now we are going to show that this is the norm, and for that we need to validate few properties on Rn. We have to validate these three properties for the definitions here. So first property we want to show it. First one. So clearly, since this is x1 square, x2 square, and xn square, so clearly this will be always positive or greater than equal 0. Okay, so clearly norm of x2 is greater than equal 0 as we have as x1 square plus x2 square x3 square plus xn square is always greater than 0 for all x1, x2, xn, and the equality 0 will happen. Okay, now x1 square plus x2 square plus xn square is equal 0 if and only if all xi is equal 0 for I is equal 1 to up to n. So therefore, if all xi is 0, that means norm of x2 is equal 0 if and only if x is equal 0. Now come to the second property. So for the second property, so norm of alpha x2. So therefore, since x is equal Rn, so with x1, x2, xn are the component, so we'll have here, this will be defined as alpha x1 whole square plus alpha x2 whole square plus alpha xn whole square. So this is, we separate it, so it will be each part we can take out the alpha. So we can rewrite it as alpha square x1 square x2 square plus xn square. So alpha square can take out with the square root, so which can be written as absolute value of alpha, and then the remaining part is x1 square plus x2 square plus so on xn square. So which is nothing but this square root is same as here, so it will equal norm of x2. So this will validate the second property. Now the third one is the triangular inequality. Okay, so to verify the third property, let we have already x belongs to Rn with the component x1, x2, xn, and let y is equal y1 y2 yn belongs to Rn. Then we have x plus y is equal x1 plus y1, x2 plus y2, and xn plus yn. So therefore, norm of x plus y, this is equal, we will have here square root of x1 plus y1 whole square plus x2 plus y2 whole square plus xn plus yn whole square. So this is the definitions of norm of x, y. But we can write it here that, so this implies norm of x plus y to its whole square. So this is equal this is equal x1 square plus 2x x1 y1 plus y1 square plus x2 square plus 2 x2 y2 plus y2 square. So plus this, so on. The last one is xn square plus 2 xn yn plus yn square. So this is equal. Now we'll just take the x component and y component part. So you will get it here, x1 square plus x2 square plus xn square, then plus yn square, y2 square, yn square, and the remaining part is 2 x1 y1 plus x2 y2 plus xn y. So the first part, this part we will have here. This part is nothing but equal norm of x2 whole square. The second part, that means this term is nothing but norm of y2 whole square. And the third part, we can write it as plus 2 into inner product x1 y 1. Now since it is norm of x whole square, which should be positive, so therefore we can take this as actually less than equal absolute value of x and y1. So which is, you can say, less than equal norm of so norm of x2 whole square plus norm of y2 whole square plus 2 into absolute value of norm of x, sorry, norm is inner product of this is okay. So now this is equal, this first part will gives us norm of x2 whole square plus the second one y2 whole square, and this third one is 2 inner product x y. Okay, so now since this one, and which we can rewrite as, so this is less than equal, and this will put absolute value of x y. Now we left to this inequality with work on this. So this is by the Cauchy inequality. So we can write it here, norm of x2 whole square plus norm of y2 whole square plus 2 into norm of x norm of y. So this part is by CR inequality. This part is by CR, means Cauchy-Riemann inequality. We did it in the previous lecture. So therefore, we can write this is as norm of x2 plus, basically this is x2. So norm of x2 plus norm of y2 whole square. So therefore, by taking the square root, we will get it here. X plus y2 is less than equal norm of x2 plus norm of y2. So this complete that norm of x2 is a norm on R2. So therefore is a norm on R. Okay, now we'll come to our next problem. Is it shows that this norm of x1 is a norm on Rn. So how we'll define this? So for that we have here that x belongs to Rn, then the norm x1 is defined as sum of the absolute value of the component. And to show this norm, again we have to verify the three properties. So let's start with the first one. So first one is clearly the absolute value of any number is non-negative. Since absolute value of any number is non-negative, so norm of x1 is greater than equal 0. If norm of x1 is equal 0, then sigma I is equal 1 to n mod of xi is equal 0 if and only if all xi is equal 0, I is equal 1 to n. So this implies x is equal 0. So this validates the first property. Now for the second one, so again norm of alpha x1. So this is equal, so when we multiply by alpha, then it will be alpha x1, alpha x2, alpha xn, and then norm 1. So this is nothing but absolute value of alpha x1 plus absolute value of alpha x2 plus absolute value of alpha xn. So this is equal, we can take out the absolute value, so absolute value of alpha and absolute value of x1, absolute value of x2 plus absolute value of xn. So this is equal absolute value of alpha and then norm of x1. So this validates the second properties. And third one is easy, because we know that we know that if absolute value of a plus b is less than equal absolute value of a plus absolute value of b. So therefore, using this property, we can say that, so therefore, for x belongs to Rn, y belongs to Rn, norm of x plus y1 is equal norm of x1 plus y1, x2 plus y2, xn plus yn, norm 1. So this is equal absolute value of x1 plus y1 plus absolute value of x2 plus y2 plus absolute value of xn plus yn. Now using this inequality, we will have this is less than equal absolute value of x1 plus absolute value of y1 plus absolute value of x2 plus absolute value of y2 plus absolute value of xn plus absolute value of yn. So which is equal absolute value of x1 plus absolute value of x2 plus absolute value of xn plus absolute value of y1 plus absolute value of y2 plus absolute value of yn. So this is equal now norm of x1 plus norm of y1. So we validate the triangular inequality. So therefore norm of x plus y1 is less than equal norm of x1 plus norm of y1. So this conclude that norm x1 is a norm on R. Okay, our next theorem is about the reverse triangular inequality, and in this part we are going to prove the reverse part of the triangular inequality, and that's a very easy proof. And so it is the basic idea of norm will gives us the proof. So let's norm of u, this is we can write as norm of u minus v plus v. So now this norm is norm 2, norm 1, for anyone we can apply it. So this is less than equal by the triangular inequality. This can be written as less than equal norm of u minus v plus norm of v. it is by triangular inequality. This implies norm of u minus v, which is greater than equal norm of u minus norm of. Similarly, if we start with v, so norm of v is equal, this is norm of v minus u, then plus u, and this can be written as norm of v minus u plus norm of u. Now v minus u will be same as u minus v, so this implies, you can write it, norm of v minus u, which is again equal to norm of u minus v, will be less than equal. Now in this case, this is equal norm of, in this case it is equal norm of v norm of v minus norm of u, which is equivalent to say minus norm of u minus norm of, we wrote it, this is to show that this and this are the part of absolute value. Now togetherly, this is 1 and this is 2. Now combining 1 and 2, we'll get it here. Look on this, this is u minus v, so this is u minus v, this is also u minus v, and here is u minus norm of u minus norm of v, and here is minus of norm of u norm of v. So therefore this two part will gives us the absolute value of u. So therefore these two will combinedly gives you norm of u minus v is greater than equal norm of mod of norm of u minus norm of v, and this proves the reverse triangular inequality. Our next is, we have here the parallelogram law for vector x and y in Rn. So this is also another easy proof, and for that we need to recall about the relation between the norm and inner product. So norm of x is whole square, this can be written as inner product of x. So we utilize this relation and we'll prove this parallelogram law. So therefore we can write it here. The norm of, so norm of x minus y whole square plus norm of x plus y whole square. So this is the inner product x minus y plus the inner product x plus y. So this is equal. Now we'll use the properties of the inner product and we'll simplify more. So this can be written as x x inner product plus x minus y plus minus y x and plus inner product of minus y minus. Same way, the second part you will have here x inner product plus x y inner product plus y x inner product plus y y. So now here is this part will have minus and this part minus, which will came out, and here minus and minus which become plus. So therefore we can rewrite this as inner product x minus inner product xy plus, this is also minus inner product yx, and this is plus inner product y, and repeat the same terms, xx plus xy plus yx plus y. So this is equal. Now here norm xx, norm xx, so inner product xx, inner product xx, so therefore it will become 2 inner product xx, and then this will cancel out and you will have plus 2 inner product y y. So xx again, by this we'll have 2 of norm of x whole square plus 2 of norm of y whole square, and this will get the parallelogram law.
We are going to solve a problem where we consider two vectors from R3 and then which we denoted as x and y. Then we are going to find norm of x, norm of y, norm of x plus y, norm of x minus y, and the inner product x minus y. And then we are going to verify the Cauchy Schwarz inequality, triangular inequality, and parallelogram law. And then we'll find the x infinity norm and x1 norm and prove the corresponding inequality, which is actually to show the equivalency. So first let's have norm of x, and we know that it is x1 square, x2 square, x3 square, means component square and then square root. So which 1 square plus 0 square plus 2 square, so which is square root of 5. Then come to the norm of y with the same idea, same formula, and then it is will give as 3 square plus minus 1 square plus 1 square, so which is square root 11. Now when we take x plus y, then we have to first take the component addition square, and with the same formula we will get here square root of 26. And x minus y, we have to subtract component wise and apply the same formula, and we will get square root 6. Now the inner product is the component multiplications, and then add them, then we will get this number as 1301 and 2 multiply 1, which is equal 5. Then the Cauchy Schwarz inequality, which is given a absolute value of inner product xy is less than equal norm of x and norm of y. Then we already calculate inner product of xy, which is equal 5. Norm of x is equal square root 5 and norm of y equal square root 11. Then if we calculate norm of x multiply norm of y, which is square root 55, and then in calculating we get 7.4161984871. So therefore it is actually more than 7 value, and absolute value of the inner product is equal 5. So therefore obviously this is uh, a hold, but this is not equal, this is less than. Same way, triangular inequality, which is written as norm of x plus y less than equal norm of x plus norm of y. Again, all the calculation is done. So norm of x plus y equal to square root of 26, which is 5.099. Norm of x is square root 5, norm of y equal to square root 11. So if you add them, norm of x plus norm of y, which is given as 5.552, and then clearly that square x plus y is 5.099, so it will be less than of norm of x plus norm of y. So in this case also equality does not hold, only the less than. Now the parallelogram law, this formula is given here, and all the norms we already calculated, and that's our square root 26, x minus y is square root 6, norm of x equal square root 5, norm of y equal square root 11. Then if you take the left hand side, norm of x minus 1 whole square, x plus y whole square, which is come 32. And then we'll take the right hand side, and if you see that it is also coming 32. So therefore the parallelogram law holds here. Now norm of x infinity, which is maximum of the component, and it is 102, so equal to, and we already know that 2 less than square root 5 less than 2 square root 3, which is equivalent to say norm of x infinity less than equal norm of x less than equal square root 3 x infinity. Same way, norm of x1, which is the sum of the component 1 plus 0 plus 2 is equal 3. So this will gives you 3 square root 3 less than square root 5 less than 3. So which is equivalent to 1 over square root 3 norm of x1 less than equal norm of